Reactions involving gases. We've talked about gas evolution reactions, combustion reactions. These sorts of reactions can have gases as reactants and or products. And so when we specify the amount of gas as a reactant or product, we typically express its volume, pressure, and temperature instead of its mass, because gases are difficult to weigh. So we can use the ideal gas law to calculate the amount of gas in moles if we know the pressure, the volume, and the temperature. If we are trying to find the volume of gas that's given off, we can use the ideal gas law as well if we've got the moles of gas from our calculation, the temperature, and the pressure. If you've got that magical phrase at STP, gases at, I wanted the highlighter that time. Gases at STP, we can use 1 mole equals 22.4 liters. That makes the calculation a lot faster. But you can only use that at STP and only for gases. People get a little too involved with 22.4 and they try to use it for liquids, and that's just absolutely not even close to true. The pressures that we have here, it might be the only gas in the mixture, so it could be the total pressure, but a lot of times it's a partial pressure. So our regular stoichiometry path was grams to moles to moles to grams. So grams to moles to moles to grams. And so this is a variation. We always have moles to moles in the middle. Always. Sometimes that's all we've got. We're just going from moles of one thing to moles of another. Don't try to complicate it. At the ends, we've got lots of different possibilities. We've done solution chemistry, solution stoichiometry, and so we could have a volume here and use the molarity to convert to moles, and that could happen at the end. And now with gases, we can have the pressure, volume, and temperature of a gas and use that to convert to moles. And then at the end, we could end up with grams, or we might convert to pressure, volume, temperature of a gas. Okay, so we're just switching up the ends. Well, here's an example. In the following reaction, 4.58 liters of oxygen was formed at pressure equals 745 millimeters of mercury, and T equals 308 Kelvin. How many grams of Ag2O decomposed? So the big clue that this is a stoichiometry problem is that I have a chemical reaction going on here. It's not talking about I changed the temperature of the gas or anything like that. I've got a reaction. And so I'm going to use that chemical equation to organize the information. So under O2, I'm going to write 4.58 liters, because that's what it's told me the volume was. And then it says that volume at, and gives me the pressure and temperature. So I'm going to write those down here as well. And 308 Kelvin. So this is the volume, this is the pressure, and this is the temperature. And then the question, how many grams of Ag2O? So Ag2O, question mark, grams. Okay? So stoichiometry, we start with grams to moles to grams. So here I have grams. This is the question, so I'm going to end with grams, so that one's fine. But here, I'm not starting with grams. I'm going to start with the pressure, the volume, and the temperature of a gas. And I can use the ideal gas law to calculate the moles from that, and then moles to moles, and then to grams. So my first task is find the moles of oxygen. Yes? So I start with grams to moles to grams, and then I see that I do need grams at the end, because that's what I'm trying to find is grams. But at the beginning, I'm not given a mass of oxygen. I'm given a volume, a pressure, and a temperature. And those are the three things I need to put into the ideal gas law, and I can calculate moles. okay? So first off, I'm going to use the ideal gas law and calculate moles of oxygen. So that's pressure times volume over R times temperature. So the pressure was given in millimeters of mercury. Of course it was. So I have to convert to atmospheres. $745 divided by 760. So there's my pressure, so I can plug that into my equation. This is up too high. So pressure 0.98026 atmospheres. And the volume they gave in liters, thank you. And R and the temperature was also given in the correct unit. And so then I check here that my units are going to cancel out. Because those messy units on the ideal gas constant help us to know what units we should use on our other things. So that's going to equal getting 0.17763 moles. Anybody else get that? I heard a little noise that sounded positive. I'd like it to be yes, so I'll take it as yes. So that's moles of oxygen. So now we're here. So we can go from moles of oxygen to moles of the other thing. So moles of Ag2O, and I'm going to divide by moles of oxygen. So in this stoichiometry problem, I'm using an equation and dimensional analysis. And for moles of Ag2O, I can go to grams of Ag2O. So those cancel out. The mole ratio comes from the balanced chemical equation. There's a 1 in front of the O2 that isn't written, and a 2 in front of the silver oxide. 2 silver oxide, 1 mole of oxygen. And then I have to calculate the molar mass. 107.9 plus 16. $231.8. So 1 mole weighs 231.8 grams. So I've got my moles of oxygen times 2 times 231.8. Yeah?
You have 1 mole of O2 at the bottom, and then you have 2 moles of, okay, you have Ag2. Sorry, never mind.
Okay.
I thought you wrote 2 moles of Ag.
Yeah. Yeah, it would be, if it was Ag, it'd be 4. So 82.35, which would round up to 4. Anybody else get that? So it would take that many grams of the silver oxide. Any questions? These problems do take some time. And so one way to speed things up for an exam is we may just give you all of the variables with the correct units. That speeds things up. And then sometimes we'll just hand you the molar mass so you don't have to take time dealing with that. And then you can just put the pieces together and it goes much faster. 82.3. So what if we've got at STP, let's do an example of that. How many liters of oxygen at STP are required to form 10.5 grams of water? So 10.5 grams of water, and the question is how many liters of oxygen? Question mark, liters. It says at STP. So then I can use 22.4 liters is equal to 1 mole because it said STP. So regular path would be grams to moles to moles to grams. The thing I'm starting with is in grams, so that's fine, grams to moles, but then at the end I want to find liters. So instead of grams here, I'm going to find liters. Because this is at STP and I've got the molar volume of a gas, I don't have to use the ideal gas law. I can just use the molar volume of a gas to convert between moles and liters. You could, if you forget how to do that or that it exists, you can use the ideal gas law still. You can get your moles here and then you can calculate the volume. You still have to recognize that STP means 1 atmosphere and 273 Kelvin. So 10.5 grams of water. I've got 3 arrows. I'm going to have 3 conversion factors. So I'm going to go to moles of H2O, and grams of H2O will come down here. And then next I'm going to moles of oxygen, and moles of H2O down here. And then I'm going to go to liters of oxygen, and moles down here. So liters to moles at STP, 22.4 liters is 1 mole. The mole ratio, 1 mole of oxygen to 2 moles of hydrogen. Dihydrogen monoxide, 2 moles of water. 2 moles of water, 1 mole of oxygen. And then over here, that's a really sad looking, that O is bad too. I need the molar mass of water. I've got that one in my head. Oops. 10.5 divided by 18.016 divided by 2 times 22.4. 6.53. Any questions?
I would only use 22.4 when they're talking about gases.
Yes. You can only use 22.4 liters per mole for gases at STP. It has to be a gas and it has to be at STP. Yeah.
How would it look if you did PV?
Yeah, so if you were going to use PV equals nRT, you'd stop here with moles of oxygen. And so that's your N. And then your temperature is 273 Kelvin. Your pressure is 1 atmosphere. And then you're going to solve for volume. $6.53.
Oh,
Yeah.
will you give us, or should we just remember that 1 moles really are at STP?
That'll be on that list of things. Yeah. Mm-hmm.
How would you set up, because you said you could use the ideal gas law and remember the moles to liters, how would you set it up?
So I'd stop here, and I'd end up with moles of oxygen. So that's N. From what they say here, STP, I know that T equals 273 Kelvin and pressure equals 1 atmosphere, because that's the definition of STP. So then I've got PV equals nRT, and I'm going to solve for the volume. So the volume is going to equal to nRT, divided by P. And I've got N and I always know R and T and P. Okay?